Alright, welcome back to another AQA A-level chemistry video. Today I'm going to be doing a video on colors of ions. This is a very important video given the fact that colors of ions is one of the properties of a transition metal ion. Remember, one of the properties of transition metal ions is that they're able to form specific colored ions in solution, and you need to be able to understand how and why that is. And in this video I'm going to be breaking down what's going on both physically and chemically in a transition metal ion in order for that to happen. Now, I'm going to be very blunt. This video is very jam-packed and it may be slightly long, but I'm going to explain it as quickly as I can, but to make sure that I explain it in a way that you guys fully understand. And if you don't understand what I'm saying, please just leave a comment in the video and I'll try and break it down. So in this video, I'll explain both physically and chemically what's going on. I'll be talking about d-subshell splitting, light absorption, a couple of calculations that you need to understand. I'll be talking about a couple of examples that you need to know in terms of, you need to know a couple of colors of ions that you must know for your exam. I'm going to leave a link to Allery Chemistry because he has pretty much nearly all of them. I've only got a select few, but you need to know a couple of examples because they may not specifically ask them, but they may infer it from a question, and you need to be able to understand what's going on, what ion are these referring to, because you know how AQA like to work. They like to test your knowledge of these colors of knowledge that you need to know for exam, right? I'll then be going through a small example, or actually I'm not gonna go too much into that detail about a couple of acidic ions, but I'm not going to go into too much details about that. But what I will go into detail in is about an investigative technique that you need to know for your exam. It's called colorimetry, and you need to know how and why it works and what are the steps you need to take in order to actually get results from colorimetry to form something that we call a calibration curve. And it's important that you get a calibration curve because it can allow you to work out unknown concentrations of a sample using the absorbance of light from that sample. It's a very unique technique, and you need to understand how and why you get to that final stage of working out the unknown concentration, because it can be turned up as a 6 marker in your exam where they ask you explain how somebody can work out the unknown concentration of this sample using a series of solutions, right? It's this video is going to have a lot in it, and I'm going to try and break it down as best as I can. So without further ado, I'm going to go straight into this video, right? So the color of transition metal ions depends on d-subshell splitting. The color of transition metal ions depends on their ligands and their geometries. So splitting. So without ligands, all of the d orbitals have the same energy, and in the presence of ligands, the orbitals will split. Some of them gain energy and some of them lose energy. This is shown in the following diagram that's below, and I'll show you it. The difference in energy of the upper level and the lower level is given by the symbol delta E, right? I'm going to break this down. So I'm going to read a bit and I'm going to break it down each time, right? So what's actually going on here? Because maybe you got really confused what's actually been talked to. I'm going to break everything down, right? So forgetting about splitting or anything like that, right? All transition metals have electrons in the d orbital. You should know that by now, right? All electrons have, as they are, transition metals have their final electrons in the d orbital. What you need to understand is that all of those electrons in d orbitals have the same, or all of the d orbitals in general have the same energy as they are. Now, ligands, and you should know what a ligand is. It's just an atom or a compound that's able to donate a lone pair of electrons to a transition metal ion, and form a coordinate bond, forming a transition metal complex. You should know that by now. But ligands have this very, very unique property where they're able to actually split the d orbital. And when they split the d orbital, some of the orbitals will, so when that orbital splits, that one of the parts of the orbital will gain energy and one of the parts of the orbital will lose energy, and it'll form this gap. It'll form this difference in energy, this kind of gap that allows electrons to flow in between it. But these orbitals are split, right? And what happens is that you form this kind of this small gap, and we call this gap an energy gap, because what's actually going on here is that electrons are going to be able to be excited or de-excited, and in order for that to happen, you need to be able to either reach or exceed this energy gap. If you reach or exceed the energy gap, you're able to excite electrons to a higher energy level, and those electrons can then de-excite back to the lower energy level. But as they do so, they release energy. And I'm going to explain that in a bit more detail. But for the most important part here is that you understand that ligands cause a very unique property where they're able to split the d orbitals, and when those d orbitals get split, so one part of the orbital will gain energy and one part of the orbital will lose some energy, and it'll form an energy gap, right? And that energy gap is given by the symbol delta E. You should know from maths that delta is the Greek symbol used to represent difference, and E is just used to represent energy. Now I'll use it pictorially here because maybe you didn't understand. I'll show you pictures and diagrams to help you understand, right? In case you're still not understanding. So I'm using Cu2 plus here as an example, right? Because it's a good example to show. Cu2 plus, this is what it looks like, right? This is the electronic configuration in terms of the box method, right? 7 electrons in the outermost shell, right? When we split this, so as it is, it will stay like this. When we introduce a ligand, let's just say water ligand, what actually happens is that it causes this d orbital to split. And so let's say we split it by here, right? Let's say we split it by there. Now, it may be that this gains energy and this loses energy. It could be the other way around, whatever, right? But one part of the orbital will lose energy, one part of the orbital will gain energy. I'm going to represent it like so. So I'll show this part of the orbital gains it. And you don't need to understand which one gains energy, which one loses energy. I think there is a way to work it out, but you don't need to know that for A level, at that level of A level. All you need to know is that one of them gains energy, one of them loses energy. That's all you need to know at this level. And once you do that, we form something here called an energy gap. So let me just finish off that. And this gap here is the energy gap, the difference in energy between the two orbitals. Now I'm going to go explain in a bit more detail what's going on in this next part here, right? So, light absorption. So, what's actually going on? How is this relevant to light being absorbed and what color we see from a transition metal, right? This shows you, I'm just talking about an energy gap. You're probably thinking to yourself, how is that relevant to the color? So, color is, as you know, if you know a basic level of physics, you should know that color as we see it is just about the way light interacts with a compound and how a specific wavelength of light is being absorbed from that compound and what's being reflected back, right? So electrons will occupy the lower energy orbital first, and this is called the ground electronic state of the ion. If an electron absorbs energy equal to that of the energy gap, it can move to occupy the higher energy orbitals, and this is called the excited electronic state. Electrons will absorb frequencies of light that contain enough energy to jump the energy gap, right? And this is shown pictorially above. So I'm going to bring back this example here, right, of the Cu2 plus, right? So as I said, it's not completely random, but you don't need to understand which part of the orbital will gain energy, which one will lose energy. Doesn't matter, right? But what you need to know is that the one that loses energy, we call this the ground electronic. So this part of the orbital here, where these electrons in this low orbital are called the ground electronic state, and these electrons in this high energy orbital here are called the excited electronic state. I'm not going to go and write that down every single time, but excited electronic state, ground electronic state, right? Now, what happens is that in order for an electron, we want what's essentially happening here is, in the presence of light, of course, in a dark room, you're not going to be able to see anything because there's no light there for to breach this gap here, right? But when there's in the presence of light, the electrons will absorb. The electrons need to basically absorb. I'm kind of waffling too much here. Essentially, what's going on here, right, is that we're trying to get this electron, one of these electrons, to be excited to this orbital here, right? So in order for that to do so, it needs to gain energy, but in particular, it needs to gain energy equal to, so energy needs to be equal to or more than this energy gap in order for this electron to be excited, right, to this higher energy orbital. Think of it like an activation energy. It needs to be equal to or greater than the energy needs to be equal to or greater than the activation energy in order for a reaction to happen, right? And it's just the same principle here, but with the electron, where the energy needs to be greater than or equal to the energy gap in order for the electron to be excited to that higher energy orbital. Good. I hope you get that point right now. So how is that? Where is this electron gaining this energy from? It's gaining energy from a specific frequency of light. So it's absorbed. First of all, this compound will absorb a specific wavelength of light, but that wavelength of light needs to be of a particular frequency. So it's absorbing energy in forms of frequencies of light, right? So for example, copper 2 plus, right? I'm going to use an example of in solution, copper 2 plus is going to be copper hexaaqua, and copper hexaaqua actually absorbs yellow light in particular. So it will absorb the yellow wavelength of light, but that wavelength of light needs to be of a specific frequency. It needs to have, and it needs that in order to, it needs to have that frequency, because it has that when it's of that frequency, it has energy greater than or equal to the energy gap, and that allows the electron to be excited to this higher energy orbital here, right? Now, as I said, it's absorbing yellow light, which means that it's reflecting back all other wavelengths of light, right? So good, that's one part of it. So now we have this electron gets to this. So let's say we're able to get this electron to here, right? And it comes to like that, right? So now what happens is that this electron then de-excites back from, so originally the electron gets excited from the ground electronic state to the excited electronic state, and then it gets de-excited from the excited electronic state back down to the ground electronic state. As it does so, it releases back a specific wavelength of light, or emits a specific wavelength of light. Together with the other wavelengths of light, we call that is the light that we see, right? So obviously the yellow, we don't see any yellow because that gets absorbed, right? I'm not going to go through the entire visible light spectrum, mostly because I don't know all of them in which order they go in, but I know it's not like this. Let's just chuck some in there, just green and blue, whatever, right? Violet, just chuck in. I don't know I forgot the order, but let's just say it's absorbing yellow, it's reflecting back everything else, and as this electron gets de-excited, remember it's going from an excited state of high energy electron in a high energy orbital, it's de-excited back down to a lower energy orbital, so it's losing energy. It needs to be able to lose that energy to come back down to this ground electronic state, so it releases the energy. But as remember, it has to release the energy in a specific type. It can't just release energy as it needs to release energy in a specific way, in some sort of format. And it's releasing this energy in form of a specific wavelength of light. Now, altogether, with the emitted light and the light that gets reflected back, that we call that the complementary color. Because and in this case, copper, if you ever seen hydrated copper 2 sulfate, i.e. copper 2 hexaaqua, it's blue. So that blue color is built up of or kind of a little bit of the red. It's mostly red kind of gone as well with the yellow. The red kind of absorbed with the yellow, but it's the green, the blue, the violet, all together. We call that the complementary color, right? Again, you don't need to know too much about. I don't think I have to explain too much about complementary color, but I'm just saying that so you understand what's actually physically going on. But the complementary color is all the colors together that make up the color that you see. Now, the overall color that you see is blue, but that blue is made up of a bit of green, a bit of violet, a tad bit of red, a tad bit of orange, and as well as other colors. But the overall color that you see is blue, but we call that overall color the complementary color, right? So I've kind of explained, hopefully I've explained that. I should have probably used this example because it's probably a lot better. But to clear it up in case I've overcomplicated it for you guys, simple as this is the energy gap. This needs to be of a specific frequency of light, right? This is visible light. You can see its wavelength. This is a specific wavelength of light, but it has a frequency that possesses energy greater than or equal to the energy gap, right? So it's energy that's greater than or equal to the energy gap, right? Remember what waves are. Waves just transfer energy. That's all you need to know. They just transfer energy. And in this case, it needs to make sure that that frequency is of, that wavelength of light is of a particular frequency, i.e. it possesses enough energy that's greater than or equal to the energy gap in order to excite an electron from this orbital to the higher energy orbital and cause that electron to then get de-excited back down to the ground electronic state. And as it does that, it emits a specific color, a wavelength of light, and that's the part of the color that you see, part of the complementary color. All right, so hopefully that all made sense. And is there anything that I can say here? No, I will say one more thing before I move on to the next part. There is a question that comes up in the exam, and it sometimes comes up in exam, and it's actually a very simple question. It's a 1-mark question, and it comes up, and it will say to yourself, why is it that zinc doesn't present, for example, why is it that you can tell that zinc isn't able to, or so why is, so I'm kind of muddling my words right now. I apologize for that one. Why wouldn't zinc possess the same properties in terms of colors of ions as copper 2+, or as copper, or as any other transition metal ion? Now you should know that zinc isn't considered a transition metal ion. It's just a D block atom, or an atom in the D block. So it's a very, very simple answer for this. It wouldn't actually possess this property because, that is zinc. So that's copper here. Now I'm going to show you what this is, the electronic configuration of the 3D orbital of zinc, right? It looks like this. I should have done it like that first, and then, oh well. Now, looking at this, I want you to think in your head, why would zinc not be able to show the same property as this copper 2+, right? Why would it not be able to do that? And it's a very simple answer. It's the fact that zinc, for copper 2+, we're saying that the electrons are getting excited. The d orbital is getting split, and the electrons once this orbital splits, we're forming this clear, and we're forming a higher energy orbital and a lower energy orbital, and that forms an energy gap, right? But more importantly, there's the electrons, because this energy gap here, we form the energy gap, but the energy gap is useful to us because it allows electrons to be excited from a lower energy orbital to a higher energy orbital. But in zinc, all of the orbitals are full. Remember, a transition metal ion has a partially filled d subshell. There's a reason for that. It's not just because it sounds nice. It's because it's part of the definition, because it directly relates to the properties that it has. So it's an oxidation state, catalyst, forming colored ions in this case. Because